Hi students, in the last video we discussed about the packing of crystals, how to pack the constituents inside the crystal lattice. So we also discussed about its packing in one dimension, two-dimensional way of packing, and also it has been applied to three-dimension for simple cubic arrangement and body-centered cubic arrangement. Also about the packing efficiencies, about the simple cubic, body-centered cubic. So in this video we are going to discuss about the arrangement of the constituents in hexagonal packing and also in face-centered cubic arrangement. So this hexagonal and face-centered cubic arrangement can be done by packing it in three ways, that is in three layers. First one is the formation of the first layer. So we can imagine it like a sandwich, layer by layer, how we are arranging, like that we can imagine. So in the formation of the first layer, we are just following the two-dimensional way of arrangement, that is AB type arrangement. So this AB type arrangement is nothing but in the first layer we are just arranging the spheres in one dimension, that is in linear arrangement. And the second row is arranged in such a way that they exactly fit in the depression of the first layer. Since it is different, it is designated as B. Okay, and then the third layer is arranged which is similar to that of the A, and fourth layer is arranged similar to that of the second layer B. So this pattern is repeated and this can be termed as AB type arrangement. And now this has been packed and this can be treated as the first layer, so we can keep it in a horizontal way, and this first layer is designated as small a. Okay, and the second layer, formation of the second layer, and this second layer is based on the voids or holes which is formed in the first layer. So in the first layer, which we have placed it horizontally, it consists of two types of voids or holes. So they are nothing but X and Y. So based on this void, we are going to form the second layer. So we can arrange the second layer either on the voids of X or on the voids of Y. Suppose we can arrange, or we can consider the arrangement of the second layer on the voids X. So when we place the spheres on the first layer, that is on the voids of X, we can able to form a tetrahedron. When all the four corners are joined, we can able to get a tetrahedron. So that constitutes four spheres, and the three spheres are in the lower layer, which is in the first layer A, and one sphere is present in the upper layer, that is in the second layer, and it is B. Okay, and here the voids, at the same time we have just placed the spheres on the voids X. So it is partially, the spheres what we have placed on X, they partially cover the voids Y. Okay, and the voids which is placed in the placed by the spheres in the layer B. In such a way, an octahedral void is formed. So octahedral, we can consider 6 spheres. So it is constituting 6 spheres, 3 in the lower layer, that is in the first layer A, and 3 in the upper layer B. Okay, and also simultaneously during this arrangement of the second layer, one more tetrahedral void is also formed in the second layer. So that is about the formation of the second layer. So just we have placed the first layer, it is a small a, and the second layer we have placed, it is designated as B. And then the third layer, formation of the third layer. So this formation of the third layer can take place in two ways. One is ABA arrangement and then ABC arrangement. When ABA arrangement is taking place, that structure, it is leading to HCP structure. HCP, hexagonal closed packing structure. When we follow ABC arrangement, it leads to CCP structure, that is cubic closed packed structure. So we will just see one by one what is ABA arrangement and what is ABC arrangement. First, in the case of ABA arrangement, see just we have placed the first layer and in the depression of the first layer we have placed the second layer, and we are going to place the third layer in the depressions of the second layer such that the tetrahedral voids of the second layer are covered by the spheres of the third layer. Now the third layer is directly fitted over the first layer. So the third layer what we have placed is similar to that of the first layer. So the pattern followed is ABA arrangement, and this type of arrangement is known as HCP arrangement, hexagonal close packed arrangement. So this is one way of arranging the third layer. So first we have placed the first layer A, and then second layer on the voids, and then again we have placed the first layer. So like a sandwich we can imagine ABA arrangement, and this structure leads to HCP arrangement. Okay, and then the second way of arranging the third layer is ABC arrangement. So in this ABC arrangement we have placed the first layer, and we have arranged the second layer on the voids of the first layer, and see we have placed this first layer as A, second layer in the depression of the first layer B, and then we are placing the third layer on the depressions of the second layer in such a way the octahedral voids of the second layer are covered by the spheres which is present in the third layer. So this third layer is fitted in the depression of the second layer. It is totally different from that of the first layer. See, this is different, totally different from that of the first layer. So we are designating this as A first layer, second layer as B, and the third layer as C. And this type of arrangement, if we repeat, or if the stacking of the crystal continues like this A, B, C, A, B, C, then that type of arrangement is known as CCP structure, cubic close packed structure. And the coordination number for this hexagonal close packing arrangement is 12. That is, 6 spheres are arranged in its own layer, and 3 spheres are lying above the plane, and 3 spheres are lying in the below the plane. Okay, so that is about the arrangement of close pack, hexagonal close packed structure and cubic close packed structure based on the layers. And generally, if the number of close packed spheres, if it is considered as n, then we can able to calculate the voids, that is voids generated in that packing. So if the close packed spheres is assumed as n, then the number of octahedral voids are equated to n, or the number of octahedral voids generated will be n, then the number of tetrahedral voids generated will be twice its amount, that is 2n. So based on this we can able to calculate the number of voids, that is both octahedral voids as well as the number of tetrahedral voids. Next we will discuss about the packing efficiency for face-centered cubic system, FCC. So here we have we are seeing the diagram for FCC. Here the atoms are arranged along the edges as well as the center of each face, and the atoms which are present along the edges, they are not in contact with each other, but these edge atoms, they are in contact with the one which is present at the center of each face. So from the diagram here we can able to see a triangle ABC. So this hypotenuse, its value is given as 4r, because the center sphere is carrying the diameter 2r, and the edge spheres, the 2 edge spheres are having the radius r. So totally the AC distance is equal to 4r, and this 4r can be calculated as a root 2. So this a root 2 can be calculated by considering the triangle ABC. So according to the Pythagoras theorem, it is calculated as the hypotenuse square is equal to the sum of the adjacent side square and opposite side square. So AC is given as square root of AB square plus BC square. And we know this is a cubic system whose edge length is given as A, and all the 3 edge lengths are equal. since all the three are equal, we can consider this distance as A, and AB is considered as small a, and even BC is considered as A. So substituting those values here, we are getting the AC value as root 2A. Now substituting this AC value here, so 4R is equated to A root 2. From this we can able to find out the radius R is equal to A root 2 by 4. And we know the volume of the sphere which is containing radius R, it is 4 by 3 pi R cube. Now substituting this radius value here, on simplification you are getting 4 by 3 pi 2 root 2 A cube by 64. So finally it is given as root 2 A cube pi by 24, and we know the total number of atoms per unit cell for FCC, it is given as 4. So based on this, the volume of all the spheres in FCC can be calculated as 4 into the volume what we have calculated in the previous step, that is root 2 pi A cube by 24. So this on further simplification gives you root 2 pi A cube by 6. So we got the total volume, and we know the volume of the unit cell whose edge length is equal, that is given as A cube. So finally the packing efficiency can be taken as the ratio of the total volume what we have calculated for all these spheres to the volume of the unit cell whose edge length is A. So this on further simplification gives root 2 pi by 6 into 100. So we know the value of root 2, it is 1.414, and the value of pi, which is 3.14 divided by 6, everything into 100. So this on further simplification gives you 74%. So the packing efficiency for FCC is 74%. That means 74% of the space inside the crystal is occupied by the spheres, leaving the remaining space empty, and this packing is said to be the efficient packing when compared to simple cubic and body centered cubic. Next we'll discuss about the radius ratio. So this radius ratio value gives you, or it can able to find out the structure of an ionic compound, especially that is for ionic crystal we can able to predict the structure using this radius ratio. So this structure what we are going to find out, that depends on the two factors, on a stoichiometry of the crystal, that is a balancing of the ions, and then the size of the ions. And as we know, in the ionic crystal the cation size is very small and the size of anion is very large, and this is assumed according to the Fajan's rule. Okay, and this ratio, that is the radius ratio between the radius of the cation and the radius of the anion, this ratio determines the structure of an ionic compound. So based on the values what we are seeing here, we can able to predict the structure of the ionic compound with different coordination numbers. So here we are seeing a table of the radius ratio in different limits. Suppose if the radius ratio is lying between 0.155 to 0.225, then its corresponding coordination number will be 3, and the structure is assumed as trigonal planar. And the best example for this type is boron oxide, that is B2O3. Next, if the radius ratio lies between 0.225 to 0.414, then the coordination number is 4 and the structure is assumed as tetrahedral. And the best example for this type of crystal is we can consider zinc sulfide. And next, if the radius ratio lies between 0.414 to 0.732, then the coordination number is 6, and we know whenever we get the coordination number 6, the corresponding structure will be octahedral, and the best example for this type is sodium chloride crystal. And finally, if the radius ratio is lying between 0.732 to 1.0, then its coordination number will be 8, and the structure is considered as cubic arrangement, and the best example for this type is cesium chloride crystal. So that is about radius ratio, which helps to determine the structure of an ionic crystal or ionic compound. Next, a very important topic is about imperfections in solids. So in the last topic we have discussed about the packing of crystals in different ways, that is in 1 dimension, in 2 dimension, and that is extended to 3 dimension for all the cubic arrangements we have seen. Next, during this packing of crystals, definitely there will be imperfection or defects in the solids. And as we know, according to the law of nature, nothing is perfect in this world, so everything has some defects. So same concept can be applied to the packing of crystals, that is during that packing we are getting some defects. So the imperfections or defects in the crystals or in solids can be due to 2 reasons. One is due to crystal packing and the other one is due to thermal vibrations, because when you just heat the crystal, the constituents which are present in the lattice points, they undergo some vibrations, and because of the vibrations some ions can be missed from the lattice points or some ions can dislocate from its lattice points. So because of that, defects can arise in the crystals. And there are 4 common defects for the crystal. They are point defects, line defects, volume defects and interstitial defects. So out of all these 4 defects, the most important defect is point defect. So next we are going to discuss about this point defect. Next we will discuss about point defect. As I told you, among the 4 point defects, the most common one is point defect. Here the point defect is discussed in the case of ionic solids. So the point defect can be broadly classified into 3 types: stoichiometry defect, non-stoichiometry defect and impurity defect. So this stoichiometric defect is further classified into Schottky defect and Frenkel defect, and non-stoichiometric defect can be further classified into metal excess defect and metal deficient defect. Now coming to the stoichiometric defect. Stoichiometry, it is nothing but the balancing of the ions. In this case, the defect can arise due to the missing of ions or can be arise due to dislocation of ions, etc. So this stoichiometric defect is otherwise known as intrinsic defect or thermodynamic defect, because this stoichiometry defect can arise due to thermal vibration. So first, these 2 defects, which is Schottky defect and Frenkel defect, these 2 defects are considered as most common point defects, and the metal excess and metal deficient defects are considered as less common point defects. So first we will discuss about Schottky defect. So in this Schottky defect, there may be missing of ions from the crystal lattice. So the missing of cation will be equal to missing of anions. So the missing of ions will be equal in this case. Since the ions are missing equally, there is no change in the stoichiometry. So the crystal remains neutral, and moreover the cation and anion, its size, it remains almost same. Even though there is some difference in the size, but it is almost similar in the size. And the best example to explain this Schottky defect, we can show sodium chloride structure. So here in this sodium chloride structure, there is 2 types of vacancies created here. One is due to missing of one Na plus ion, and the other vacancy is due to missing of one Cl minus ion. So here the 2 vacancies are since equal in number, the crystal remains neutral, and also the stoichiometry remains same. And because of this Frenkel defect, it lowers the density of the crystal. For example, to say vanadium monoxide or vanadium oxide. For this crystal, the calculated density value for this one is, according to the edge length, it is 6.5 gram per centimeter cube. but the experimental density value what we have got by doing the experiment, it is about 5.6 gram per centimeter cube. So based on these two deviation in the value, we can able to predict that is vanadium monoxide is containing 14% Schottky defect. So it is just lowering the density of the crystal. So that is about the Schottky defect, which is due to missing of the ions. Next, the next common point defect is stoichiometry defect is Frenkel defect. So here the Frenkel defect, since it is also coming under stoichiometry defect, here due to thermal vibration, maybe the ions may dislocate. So here the dislocation of the ions are taking place. So the missing ions which is leaving from the lattice point, it goes and occupies the interstitial position. The interstitial position is nothing but the space between the lattice planes, that is known as interstitial space. So the ion which is leaving the crystal lattice is occupying the interstitial position. And also the crystal is remaining neutral because there is no ion, because no ion is leaving the crystal. It is remaining inside the crystal, just it is leaving its lattice point and it is present in the interstitial position. And in this case the stoichiometry is also maintained. But the size of the cation and anion are not similar, but the size of anion is somewhat larger when compared to the cation. And the best example for this Frenkel defect is AgBr. So you can just see this picture, AgBr structure. Here in the crystal lattice, one of the Ag plus ion, it is occupying the interstitial position. And always the cation will leave its lattice point because its size is very small when compared to anion. So this is the best example to explain the Frenkel defect. And the next one is, so we have discussed the two common point defects, that is stoichiometry defects. So the next non-stoichiometry defect is metal excess defect. So from the name itself we can say excess. So here presence of more number of the metal ions, that is cations, will be in excess when compared to the anions, and this metal excess defect can be explained in alkali metal chlorides. That is, for example, to say we can say NaCl, KCl or lithium chloride, LiCl, etc. So in this case one metal cation is present in excess, and also a vacancy, either cationic vacancy or anionic vacancy can be created in this case. And to explain this we can consider NaCl crystal. So here when NaCl crystal is heated in the presence of sodium vapor, what happens? The sodium atom, it is ionized, the sodium atom from the vapor, it is ionized into Na plus and electron. So that sodium ion and electron, it gets deposited on the surface of the sodium chloride crystal. Now the surface is containing Na plus as well as electron. Now the Cl minus ion which is present inside the crystal, it diffuses outside and it just combines with the Na plus which is present at the surface of the crystal, and it leaves an anionic vacancy. Understood? Now this anionic vacancy, the electron which is present at the surface, the electron diffuses into the crystal and occupies the anionic vacancy which is present inside. Now the anionic vacancies which is containing unpaired electron, it is termed as F centers. And now on the surface one extra sodium ion is present. So the excess of ion is balanced by the electron which is present inside the crystal. So the crystal neutrality will be maintained. So the formula of NaCl can be given as Na1 plus X Cl, and the same effect or defect can be also observed in zinc oxide crystal. So usually the zinc oxide is colorless in nature, but when heated it gives yellow color. Here the zinc ions and electrons both gets occupied in the interstitial position. So here you can see the metal excess defect. So here instead of one anion, electron is present electron is present and one vacancy is present here. So in that vacancy electron is occupying, which is it came from the Na plus which is present on the surface. So next you can also see the zinc oxide crystal. So here this is a zinc oxide crystal. The zinc oxide is ionized into Zn2 plus half O2. So here the Zn2 plus ions and electrons, they get occupied in the interstitial space. So the crystal neutrality will be maintained. So that is about the metal excess defect. Next is metal deficiency defect. Here deficiency, so there is some deficient. So the number of cations will be less in this case when compared to the anions. And this type of defect is occurring in the crystal in which the cations are having variable oxidation state. To explain this, we can consider iron oxide crystal. So in this iron oxide crystal, iron is present in +2 oxidation state. So you can see the picture for metal deficiency here. So here one Fe2 plus ion is missing. To maintain the neutrality, it is just creating the vacancy, and to maintain the neutrality, the number of cation which is leaving, it is oxidized into twice its number. So one Fe2 plus is missing from the crystal, so twice its amount. 2 Fe2 plus ions are oxidized into Fe3 plus ions. So here when you count the number of Fe2 plus Fe3 plus with the oxide ions, the iron atoms will be in less. So it is termed as metal deficiency defect, and the general formula for iron oxide is given as FeXO. Here the X value ranges from 0.93 to 0.98, and this is somewhat less when compared to the anions. Next, the final defect is, the final point defect is impurity defect. So this impurity defect can be explained based on the process known as doping. So as we know, doping is nothing but just introduction of some impurities to the crystal. So for example, to say, as we know, the semiconducting materials like silicon and germanium, they are just semiconductors. They can act as a good conductor when impurity is introduced into the silicon crystal or germanium crystal. So in such case, vacancies are created in the host. So finally, we can see the example, addition of cadmium chloride to the AgCl crystal. Here the cadmium which is having +2 oxidation state, it is divalent, but Ag is monovalent. So to maintain, here what happens, this Cd2 plus, when it is introduced to AgCl, it just removes one Ag plus ion from the crystal lattice and occupies its position in the crystal lattice, but the crystal neutrality is not maintained. So to maintain the neutrality, one more Ag plus ion leaves the lattice. So you can just see the picture for the impurity defect here. So this is with sodium chloride we have seen. Here Si2 plus is introduced here. Since it is divalent, the neutrality is not maintained. To maintain the neutrality, one Na plus ion is leaving the crystal lattice, so thereby maintaining the neutrality. So that is about the impurity defect. Thank you.